The next type of converter that we're going to look at is our buck-boost converter. And so we're not going to go into as much detail with this converter, but we still want to go over the highlights. So as we talked about in our overview, our buck-boost converter is capable of either increasing or decreasing our VRAW depending on certain circuit configurations and operation parameters. So looking at our circuit configuration here, again, we notice we have all these same components that we've seen in our buck and our boost converters. We have a switch, an inductor, a diode, and a capacitor. The main difference between our boost converter and this buck boost converter is we've essentially just switched our positions for our inductor and our switch. So now instead of the output voltage being across our switch, it's across our inductor. And so again, keep in mind we're neglecting any voltage drop across that diode. So because of that, our waveforms are basically going to be the same as what we saw for our boost converter, so we're not going to redraw them here. But if you want to reference that, you can see our previous video on boost converters. So same as for our boost converter. And so by waveforms, of course, I mean waveforms for our currents and our voltages that I've labeled here in the circuit. One important thing to note, though, is that we notice that the polarity of our V out is now opposite to our input voltage V raw. So using our same sort of idea of conservation of energy, we could derive an equation relating our V out to V raw. So we can say V out equals V raw times dBB divided by 1 minus dBB. And so what is our dBB? Well, our dBB is just our duty cycle for our buck boost. And that's just defined as being T on divided by our switching period T. So a similar definition to what we saw for our buck converter actually, because now our switch is back such that it is connecting input to the circuit for when it's closed and disconnecting when it's open. Okay, so one thing to note, so this top circled equation here for our V out is how it appears in your textbook, but really to be technical we should have an absolute value here because we want to note that our V naught has the opposite polarity of V raw. So V naught is opposite polarity of V raw. Okay? So our ripple voltage we can define the same way as for our boost converter. So remember for that ripple voltage in the boost converter we were assuming a constant current output. So that constant current output is I naught. We now have dBB as opposed to D boost because of course we have a different type of circuit. And then we still have our frequency and capacitance in the denominator there. So let's just say this is the same as our boost converter. Of course, like I said, the only difference is we just changed the duty cycle term, but hopefully that should be evident that we need to do that. Okay, so here's sort of our basic equation. So we're not going to go into too much more detail other than that. But one thing we do want to point out is we said that this buck boost converter can increase or decrease the input. So how do we adjust that? So let's take a closer look at this equation to see if we can't figure that out. So we sort of have three conditions. So our first condition, let's consider if we have dBB equals 0.5. So coming up here and considering this circled equation, if we look at the term in brackets, we have dBB divided by 1 minus dBB, which becomes 0.5 divided by 1 minus 0.5, which is of course just equal to 1. So we have the magnitude of V naught is equal to the magnitude of V raw. So magnitude of V naught equals V raw. And so again, we want to note that the polarities are different though. And so this is sort of one thing that makes our buck boost converter useful. So we talked about how it can kind of be considered a jack of all trades but master of none, in that our buck converter is going to be a lot better at stepping down, our boost converter is going to be a lot better at stepping up. But one instance where our buck boost converter is useful is maybe we only have positive voltages available, but we want to power something that needs positive and negative supplies, for instance an op amp. So we could use this buck boost converter to get that negative voltage from only positive voltages. So the fact that that polarity of our output is switched can actually be very useful in some applications. Okay, so coming back to how do we increase and decrease the voltage though? So we can just see if we increase our duty cycle above or below 0.5, we're going to have the desired change. So let's now consider if we have our D sub BB greater than 0.5. So in this case, we're going to end up with a V out greater than V raw. So we're going to be boosting. And on the other hand, if we decrease our dBB below 0.5, that's going to lead to our V out being less than V raw. And so again, keep in mind in both of these cases, we also have a different polarity. And so what we can see here is our duty cycle is determining whether we're increasing or decreasing. So duty cycle is controlling whether we're bucking, so decreasing, or boosting that input signal. And so that's the basic operation for our buck-boost converter.